Assalamualaikum and hi everyone. Today I will explain about assignment 2. I will introduce about our group member first. This is Afika, me Zulaika, and this is Amalia and Ifa. In assignment 2, we need to find least square solution and cure factorization by using the Gram-Smith process. We look at the equation first. First of all, the equation given the system, which means give our matrix A's and matrix B's. So the question is find the least square solution of the system AX equal to B by using the following step. A. Use the Gram-Smith process to find an orthogonal basis. Okay, so first of all, how we want to do the orthogonal basis?
So first of all, we need to find an orthogonal basis. Okay, how we want to find an orthogonal basis? First of all, we need to separate the space of A by each column, which means each column we separate as an orthogonal basis represented by the vector v1, v2, and v3. So for the column 1, we set as a vector v1. For the second column, we set as the vector v2, and the third we set as the vector v3. So then we substitute the origin basis vector v1, v2, v3 in the orthogonal basis formula, which is different between the between origin or orthogonal basis u1, u2, and u3. Okay. Orthogonal basis we represent as a u1, vector u1, vector u2, and vector u3. So for the first of all, vector u1 is the same as the vector v1. Meanwhile, vector u2, you must substitute in the formula. As you can see, we substitute in the formula. Vector v2 minus vector v2 multiplied by vector u1 divide by absolute value of the vector u1 multiply with the vector u1. And then if you substitute the values, and we will get the answer. Next we do for the ut. Okay, for the ut we have like expand the formula, which means we added another formula which is minus with vector v3 multiplied by u2 divide by absolute value of u2 square divide by multiply by u2. So if we just substitute the answer, we calculate one by one, and then we substitute the answer, then lastly we will get the answer for vector ut. That's how we obtain an orthogonal basis, which is represented by u1, u2, and u3. Next.
Okay, now I will explain how to find an orthonormal basis for the column space of matrix A using the Gram-Schmidt process. This is question 2A, and the goal is to convert the column vectors of matrix A into orthonormal vectors, which will later be used for QR factorizations. Based on my handwritten solutions, the orthogonal basis vectors u1, u2, and u3 have already been obtained. Therefore, my task at this stage is not to find the orthogonal basis again, but to convert these orthogonal vectors into an orthonormal basis. As we all know, an orthogonal basis consists of vectors that are perpendicular to each other, but their lengths are not necessarily equal to 1. Meanwhile, an orthonormal basis is obtained by normalizing each orthogonal vector so that every vector has unit length. Therefore, to obtain an orthonormal basis, we do not change the direction of the vectors. We only adjust their magnitudes. The formula used to normalize an orthogonal vector is ui equal to the vector of ui divided by the square root of the vector of ui times itself. This formula will be applied to each orthogonal vector u1, u2, and u3. Okay, now let's look at on how to find the first orthonormal vector. From my handwritten solution, the first orthogonal vector is the vector of U1 equal to the matrix of 2, 7, 4 and 3. So first, we compute the dot product of the U1 with itself. Then we divide the vector by the square root of this value. This gives the first orthonormal vector. Next, we consider the second orthogonal vector obtained earlier. Using the same normalization formula, we compute. Here, the vector of U1 times itself represents the magnitude squared of the second orthogonal vector. After substituting the values and simplifying, we obtain the second orthonormal vector as shown in my handwritten solution. Finally, we normalize the third orthogonal vector. This step ensures that the third vector also has unit length, while remaining orthogonal to the first two vectors. After calculation, we obtain the third orthonormal vector. Therefore, the orthonormal basis is obtained by normalizing each orthogonal vector. In conclusion, the steps to find an orthonormal basis are directly dependent on the orthogonal basis. We first obtain orthogonal vectors using the Gram-Schmidt process and then apply the normalization formula to each vector. This concludes my explanation. Thank you.
Okay, so now I will continue for the question B, which is solve for x by using QR factorization. Okay, we have to use the formula, which is x equal to b in brackets q transpose times r inverse, close the bracket. Q is orthonormal basis. Okay, we can see the matrix of Q that we already get from the question above. Then, if you want to find the R, we have to get Q transpose multiply with matrix A, okay, which is the Q, the matrix of Q, we have to transpose it, and then times the matrix of A, okay. Then we will get the matrix of R, which is this, and if we want to find the value of x, we have to use the formula that we already show above, which is R inverse times Q transpose times B, okay, which is we have to inverse the matrix of R, and then we will get the R inverse matrix of R and times the matrix of Q, which have been transposed above, and then times the matrix of B, and we will get the matrix, the answer, which is 1.5208 negative 1.1101 1.0721, which is x1 is 1.5208, x2 equal to negative 1.1101, and the last one, x3, we get 1.0721.
So, on this slide, I will demonstrate how QR decomposition is applied using Mathematica to solve a system of linear equations. Our goal is to find the solution vector x for the system Ax equal to b, where matrix A is a rectangular matrix with more equations than unknowns. This makes it suitable for a least square solution. First, we need to define matrix A, which is the 4 by 3 matrix, and vector B, which is for a 4 by 1 column vector. This represents a system of 4 equations with 3 unknowns. So the matrix A is 2, 6, 9, 7, 8, 6, 4, 5, 3, and 3, 8, 7, while for vector B is 7, 6, 8, 2. Next, we apply the QR decomposition A command. This decomposes matrix A into two matrices, Q and an orthogonal matrix, and R and upper triangular matrix. This factorization allows us to solve the system efficiently without directly inverting matrix A. We then use matrix form to display matrices Q and R clearly. Matrix Q has orthonormal columns while R is an upper triangular matrix which simplifies computations. To find this solution vector X, we use the formula X equal to R inverse times with Q transpose times with B. In Mathematica, this is implemented as equal to X equal to inverse R times with Q times with B. This step transforms the original system into a simpler one that can be solved directly. Since the symbolics is very complex, we apply the n function to obtain the numerical values. This approximate solution is x1 approximate to 1.52, x2 approximate to negative 1.11, and x3 approximate to 1.07. This represents the least square solution to the system. We also compute, to verify the QR decomposition, we compute Q transpose times with R. The result reconstruct the original matrix A, confirming that decomposition is correct. We also compute QR decomposition using orthogonalize as an alternative approach. This produces matrices QQ and RR. When used to solve the system, it gives the same numerical solution. This confirms the consistency and reliability of the QR method. In conclusion, QR decomposition is about a full and stable method for solving overdetermined system. Using Mathematica, we can perform this process efficiently, verify the results, and obtain accurate numerical solutions. So that's all from us. Thank you.